Ever wanted to know more about resistors and voltage?
Well, in this lab, we go over resistors and how their arrangement affects their electrical current flow. Some things to know are resistors restrict the amount of current that may flow. They are mainly used to adjust voltages and protect components. Resistance can be said to be the strength in which a component opposes current. Voltage can be the electric potential difference. Depending on the voltage will show how much charge goes through a circuit. We will also be reading resistors using their colored bands. We will also be using some equations to calculate our theoretical equivalent resistance in series and parallel. Our main goal of this experiment is to check that our resistor values match the color code numbers, test our series and parallel, and also see how combining them changes the total resistance. These are the materials we utilized during our experiment.
For this activity, we use 3 resistors connecting wires, current sensor, a voltage sensor, a signal generator, and the Capstone software. Each resistor has color-coded bands that indicate its resistance value. Our resistors for this lab are as follows. Resistor 1 with orange, white, brown, and silver bands. Resistor 2 with green, blue, orange, and silver bands. And resistor 3 with orange, yellow, and silver bands respectively. Before we begin, we record the color codes and theoretical resistance values for each resistor in our data table. We start by testing each resistor individually, connecting one resistor at a time in series with the current sensor and signal generator, and in parallel with the voltage sensor. We begin with 0 volts on the signal generator and record the current reading. Then we increase the voltage by 1 volt increments, continuing until we reach 10 volts.
We also want to make sure down here that the voltage current sensor is at 200 hertz. Also forgot to mention you want to set your x-axis to current and your y-axis to voltage. After setting up the first resistor, you want to open up Capstone and make sure you start at 0 volts. Then begin to record a sample at each voltage, starting from 0 and progressively going up to 10 volts. After taking all 10 samples, save a picture of the graph. This process on Capstone will be done for all 3 resistors individually, all 3 stacked on one another, all 3 stacked in a staircase fashion, and all 3 stacked on top of one another.
We test how resistors behave when combined.
With the top resistor hanging
We create
off.
2 setups, one where all resistors are connected in parallel, and another where they're connected in a series. Before taking measurements, we discuss as a team which configuration we think will have the greater total resistance and why. We then test both setups. We start with the parallel connection, increasing the voltage gradually from 0 to 10 volts, as previously done. We record voltage and current each time, repeating the same process for the series connection. We use the slope of each voltage versus current graph to determine the total resistance of each configuration. Again, we screenshot each graph for our report. Once both tests are complete, we compare our 2 graphs and note the difference in resistance between the series and parallel setups. To investigate further, we explore whether the order of resistors affects the total resistance. In theory, in a purely series or purely parallel connection, the order shouldn't change the result. However, if we believe otherwise, we rearrange the resistors, collect data again, and note any differences we find.
Hello, my name is Genevieve, and I'll be going over the data and data analysis. Here I calculated our resistor number 1 using our theoretical value and experimental value to get the percent error. We did 390 minus 403 over 390, and then we got 13 over 390, and then we got 0.033. We multiplied that by 100, and we got a percent error of 3.33%. For resistor number 2, this image shows our calculations. We repeated the same steps from resistor number 1. So we got the theoretical value, and we subtracted it with the experimental value. We then divided it again by the theoretical value. So the 560 minus 542, and we got 18. And then we divided that over 560. Our result was 0.032, and then we multiplied that times 100. Our percent error was 3.21%. We then repeated the same steps for resistor number 3 to obtain our results. These are our calculations. Our percent error was way off at a 974.75, so we assumed we did something wrong. We attempted to try it again, but to no avail.
This section shows our calculations for the parallel. We had to add all 3 resistors and divide by 1. Then divide by 1 again. We then used our new calculated value as the theoretical value and plugged it into the same equation used for resistors 1, 2, and 3. We got a percent error of 1.378%. For our series calculations, we used the formula of theoretical value subtracted by experimental value, and with the result we divided it by the theoretical value. Once we obtained the answer, we multiplied it by 100 to obtain our percent error of 56.01%. We came to the conclusion that one of the machines was working improperly.
For this lab, we used 3 different resistors, and each one had a color code that told us its theoretical resistance. We wrote down those values first so we can compare them later with the ones we measured during the experiment. We connected each resistor one at a time and measured the voltage and current. We started at 0, then increased by 1 up to 10 volts. And then we made a voltage versus current graph. The line on each graph came out pretty straight, which showed that the resistors followed Ohm's law. When we compared the experimental resistance to the theoretical resistance from the color codes, the numbers were close but not exactly the same. We calculated the percent error for each one, and most of them were small, showing our data was pretty accurate. The small difference probably came from loose wires or loose connection or limits on how precise our sensors were. After that, we connected all 3 resistors in series and parallel, and we collected again the voltage and current data. And we made new graphs. The slope of the line gave us the total resistance in each case. As expected, the series connection had a higher total resistance, while the parallel connection had a much smaller one. We then tested combinations where some were parallel and some were in series, and we did this 3 different times, switching the resistors. The data showed that the total resistance changed depending on which resistor was added in series. The bigger one in series, the higher overall resistance became. Our graphs and calculations matched the theory pretty well. The data clearly showed how series and parallel circuits behave differently, and how using the slope of voltage versus current graphs make it easy to find resistance accurately. Lab, we learned how to compare the resistance of resistors when they're connected in series and in parallel. The main goal was to see how voltage and current are related and how we can use the slope of voltage versus current graph to find resistance, just like Ohm's law where V equals IR. Basically, the slope of the line from our graph tells us the resistance. When we tested each resistor by itself, the graph showed a straight line relationship between voltage and current, which means they followed Ohm's law. The experimental values we got were close to the theoretical values from the color codes. Any small errors we had were probably from the things like the wires, the sensors, or just slight differences in how we connected everything. But overall, our results were pretty accurate and matched what we expected. When we connected the resistors in series, we saw that the total resistance got bigger because the current had to pass through each resistor one after another. In the parallel setup, the total resistance was smaller since the current could split into 2 different paths and move more easily. This matched what the formulas told us would happen. In series, resistance adds up, and in parallel, they combine in a way that makes the total smaller. We also tried mixing them by putting 2 resistors in parallel and 1 in series. We noticed that when we changed which resistor was in series, the total resistance changed too. The bigger the resistor we added in the series, the higher the overall resistance became. This showed that adding something in series always increases the total resistance, even if the order of the resistors changed. In conclusion, this lab helped us understand how resistors work together in circuits. Series connections make it harder for currents to flow, while parallel connections make it easier. The data we got matched the theory